Great. Our next speaker will be Jan Bormet from TU Darmstadt.
Okay, can you hear me? Nice. So hi everyone. My name is Jan, and I'm presenting today our recent work on BEAT-MEV, and this is joint work with Sebastian Faust, Hussein Othman, and Zian Ku. And in our work, we deal with the MEV problem through the means of encrypted mempools. We eliminate a single source of failure through threshold encryption, and we make use of a recent batching technique for extra efficiency and security guarantees. And also we are one of the first works to eliminate expensive per epoch setup on behalf of the committee members. But before going into details, let's quickly start with an overview of how encrypted mempools work. So in blockchains, users commonly submit their transactions to a mempool. Suppose that some user submits transaction 1 here, where he buys a large amount of some asset, let's say asset A. And there's also some other transactions in the mempool. And when it's time to make a block, a miner comes in, takes a look at the mempool, and collects transactions from the mempool, assembles them into a block, and the transactions get executed. And one problem here is, as we all know, the problem of MEV. So user 1 can observe what is the content of the transactions and see, for example, that the first transaction buys this asset A and run a front-running or sandwich attack. So in this case, he sees that the transaction buys a large amount of asset A and kind of puts the transaction before that also buys asset A, and the transaction afterwards selling asset A, running a sandwich attack, and this has some kind of downsides. So first of all, the user who sent originally transaction 1 gets worse execution prices. The miner profits from this. And also it has the side effect that transactions 4 and 5 don't get included in the block anymore. So also this creates some inefficiencies. So encrypted mempool tries to prevent this issue by, instead of having users submitting their transactions in clear, users actually encrypt their transactions to some public key, PK. And when the miner needs to assemble a block, he doesn't know what is the content of the transactions. So he needs to assemble the transactions kind of in an arbitrary order. And the idea is that he now cannot do any malicious MEV. He cannot do any front running in particular. Then once the block is assembled, we wait for finalization. And when the block is finalized, whoever obtains or whoever holds the secret key decrypts all the transactions, and the block gets executed. So clearly there's a problem, because if only one party has custody of the secret key, this party could be malicious and is basically a single point of failure, because this party could just do MEV on its own. And yeah, it could be easily bribed. We just want to avoid these kind of trusted parties. So instead, the common practice is to make use of a tool called threshold encryption. So instead of having a single party having custody of SK, we're going to assemble a committee of, in this case, 5 parties, and secret share the secret key among the committee members. So now each committee member has a secret key share. Also, we're going to set a threshold T. In this example, we set T equal to 3, such that any subset of at least 3 parties is able to decrypt transactions or ciphertext, and any malicious committee that doesn't meet the threshold. So for example, parties 1 and 2 here, it's not 3 parties, so they cannot decrypt or learn any information about the transactions. And the naive approach now is having all users just send encrypted transactions, and when the block is finalized, all the transactions are decrypted individually. And the big downside with this is that now each committee member has to release a partial decryption for every single transaction in the block. So if we have B transaction in a block, every committee member has to send messages on the order of B. And this we really want to avoid, because this causes large propagation delays and would kind of cause the system to have some trouble in keeping up with the blockchain. So we avoid this issue by trying to decrypt all the transactions at once, so not individually. And kind of common approach here is to make use of identity-based encryption, where instead of encrypting to just a public key, you can encrypt to an arbitrary tag. So suppose we're trying to encrypt to block 5. So let's say the tag is 5, and all the users have encrypted their transactions to this tag. And again, some transactions are put into the block. The block is finalized, and now the committee members just publish a decryption key for this specific tag, in this case, K5. And K5 can then be used to just decrypt all the transactions in the block. And the cool thing now is that for publishing this 5, this doesn't scale, or the communication for publishing this K5 doesn't scale with the size of the number of transactions in the block. So we kind of have better properties regarding communication efficiency on behalf of the committee members here. So far, so good. However, there's a problem, because now we've published K5, observed that transactions 6 and 7 are still in the mempool, and because they have been encrypted to the same tag, they can now also be decrypted. And now we have basically 2 transactions in the mempool, which can be observed by whoever builds the next block. So basically, the next miner can just run MEV on them. And this kind of property we want to avoid. We call this property pending transaction privacy. And what we want instead is that we want to be able to decrypt exactly the transactions in the block, but transactions that are kind of stuck in the mempool stay encrypted, so are not vulnerable to MEV. And to this end, there is some recent work by Shuduri et al. That achieves the best of both worlds. So they define a notion called batch threshold encryption that on the one hand achieves this pending transaction privacy, and also it has constant partial decryption size. So still only the transactions in the batch get decrypted, but committee members only have to kind of communicate one element. However, with their construction, there's some practical downsides. On the one hand, their construction requires recurring per epoch MPC setup among the committee members. So before users can even encrypt to a block or to some epoch, the committee members have to run some DKG-like, very expensive MPC setup. And this becomes prohibitively expensive and causes the system to kind of not being able to catch up with blocks or epoch lengths on the order of maybe 10 seconds. And at the same time, in their construction, ciphertexts are tied to a specific epoch. So at the time of encryption, a user already needs to know what block their transaction will appear in. If then a different batch has been encrypted to that block, decrypted in that block, so their transaction didn't make it, then they have to re-encrypt. So they have to kind of stay online and repeatedly send transactions every time their transaction doesn't make it. So this would just introduce some further congestion, and yeah, it's just not so nice for the users to have to do this. And in our work, we try to mitigate both of these problems. So on the one hand, we don't need any recurring setup among committee members. So we only have a single one-time setup that happens in the very beginning. And from that point, you can kind of encrypt without any setup happening before that. And also our ciphertexts are independent of an epoch. So encryptors can just encrypt. They don't need to know a tag in advance. They don't need to know which block they will appear in. And at the time of decryption, you can dynamically assemble transactions in a block and kind of decide later on which transactions make it into the same batch. So to see how we achieve this, let's look at a high-level overview of our constructions. Suppose that users 1, 2, and 3 here each want to encrypt a transaction. And we're going to start with a very simple one-template style encryption. So user 1 here encrypts message 1 by just sampling a PRF key, K1, and evaluating the PRF at index 1 in order to kind of put a mask on his message M1. And to make this decryptable, the user also attaches to a ciphertext an encryption of K1 under the public key of the committee. And the same is repeated by users 2 and 3 for their respective indices and their secret PRF keys. And to see how we decrypt, let's start with the easy example of having the batch that only contains one transaction, only C1. If the committee wants to decrypt this batch, they just use kind of in a distributed manner, decrypt this K1. And once this K1 is known, anyone can just recompute the PRF, evaluate it at index 1, and undo the mask and recover M1. Okay, so far so good. What happens if the batch is larger? Suppose we also add C3 to the batch, and now we could just repeat this process. The committee also sends K3, and we do the same thing or like we evaluate now this PRF under K3 at index 3 to also recover the third message. However, this clearly is not what we want, because now we exactly have what we wanted to avoid in the beginning. So now the committee members have to kind of communicate on the order of the batch size. So in this case, the batch size is 2, and they have to clearly send one key for every single ciphertext in the batch. So what else can we do? Let's say instead of sending K1 and K3, we use some kind of homomorphic encryption to aggregate the ciphertext and instead send a decryption of K1 plus K3. And now what happens to our decryption process? So we can now no longer evaluate the PRF under K1 because we don't know what is K1. But instead, we can evaluate the PRF under K1 plus K3. And due to some nice homomorphic property of the PRF, this is exactly equal to evaluation, or the sum of the evaluations under the two distinct keys. So the evaluation under K1 and under K3. And now we can see that this cancels out, basically this cancels out the evaluation under K1, and we are left with the message masked with the PRF evaluation under K3 at index 1. So we didn't really send K3 now, and we wanted to avoid this. So how can we get rid of this mask now? And for this, we will make use of another nice property of a PRF that we can kind of get, which is called puncturability. Suppose that user 3, who knows this K3, now also punctures his key to compute K3 star, and he punctures his key at index 3. And with a punctured key, basically you can evaluate the PRF, for example, at index 1, at index 2, but not at the punctured index. So K3 star can be used to evaluate at any index despite the punctured index 3. And this is clearly important because if we want user 3 to attach this punctured key to a ciphertext, but if it would be possible to evaluate the PRF at index 3 with the punctured key, then you could just trivially undo the mask and recover M3. So the good thing is now that we know K3 star as part of the ciphertext. During aggregation, we can just use K3 star to undo this mask and thus recover M1. And if the same is done by also user 1 and user 2, so every party also publishes a punctured key for their key and their respective index, we can actually decrypt all ciphertext in the batch with only sending a single, or like sending kind of the sum of the keys, so it's order 1 communication. And also, we want this pending transaction privacy, so let's observe what happens to message 2. So clearly, whatever the committee sent isn't at all dependent on K2. And we also know that the punctured key K2 star cannot be used to kind of undo this mask. And the other part of user 2 ciphertext, which is the encryption of K2 under the public key, is kind of remains secret if the committee doesn't release any information about K2. From this, we can deduce that kind of M2 remains private, and we get this nice or important security property of pending transaction privacy. And at the same time, observe that we didn't use any epoch setup, and also the committee member, the users didn't have to specify in the beginning which they didn't have to use some tag or they didn't have to know basically which block or like which other transactions they will be batched with. So we have kind of achieved all these properties that we wanted in the beginning. However, there's a small downside. So in order to do this punctured evaluations with this PRF, we wanted all these nice properties of puncturability and a key homomorphism from the PRF. But this means basically as a trade-off, we have that this punctured evaluation is rather expensive computationally because it requires us to compute a pairing. And yeah, pairings are rather computationally expensive group operations. So we kind of are a bit worried about aggregation time here. And this is even worse because if you scale this up to larger batches of size, for example, 100, then you will see that this aggregation step requires on the order of B squared pairing. So it's rather computationally expensive. And we will later see some techniques how we kind of mitigate this problem. But first, let's look at another detail. And this detail has to do with collisions. I've kind of glossed over or kind of assumed, without explaining why I can assume this, that every user has a single unique index or like it needs to sample this index. And one problem with this construction is that whenever there's transactions that have the same index, for example, now there's 2 transactions with index 2 and 2 transactions with index 4, then we cannot assemble these transactions into the same batch whenever there's a collision. So how we kind of would deal with this in practice is we would just have encryptors sample this unique index from a huge domain. However, another trade-off that we have from having these nice properties from the PRF is that this is not a normal PRF where the domain is exponentially large, but this domain is actually polynomially bounded, and its size somewhat relates to the size of the one-time setup we need to do in the beginning. So we cannot make this arbitrarily large. And if let's say this domain is rather small, and we have encryptors choose an index at random from this domain, there's the risk of having random collisions appearing. So how we deal with this in our work is instead of trying to decrypt all the transactions in the same batch at the same time, we just kind of open multiple sub-batches. So in this case, let's look how it works for the example of 2 sub-batches. We now, instead of trying to fit all the transactions into one batch, we assign them into sub-batches such that kind of no collisions appear within a single sub-batch. So now the transactions with index 2 are in 2 different sub-batches, and the transactions with index 4 are also in 2 different sub-batches. And basically, this means, and all of the committee members now just release decryption keys for every single sub-batch at the same time. So we have some kind of minor communication overhead now, but we are now able to deal with these collisions. And in our work, we do some analysis, and we can show that for appropriate number of sub-batches, we get reasonable statistical correctness of basically having that the probability of having collisions more collisions than the number of sub-batches in a single given index is less than 2 to the minus 40. And also a nice property of this is that this really helps with our second issue of having to compute all these punctured evaluations. Suppose that we have alpha sub-batches. Instead of having on the order of B squared pairings during aggregation, we now only need to do B times B over alpha pairings for the aggregation. So the more sub-batches we have, the less is the smaller is the probability of collisions, and also the faster aggregation gets. But we pay a small overhead in partial decryption size. And to see all of these kind of different properties in the like how they work out together, let's look quickly at the evaluation. So for encryption, we are very efficient actually. We can encrypt ciphertext in less than 2 milliseconds, and also our ciphertexts are fairly small. We have less than like an optimized version of our construction has less than 200 bytes of overhead per ciphertext, which when calculating with call data amounts to about 5 cents. Partial decryption is also rather efficient. So this means that, for example, for large batches of size 512 transactions, the work that any individual committee member has to do can be carried out in less than 300 milliseconds. And also the partial decryption size is rather small. It's just one group element, which amounts to 48 bytes. So we have some room for adding more sub-batches here. And now let's look at kind of the difficult part, the aggregation. The blue curve shows the time aggregation needs without sub-batches, and you can see that it doesn't look so nice. So even for 100 sized batches, we get aggregation times of more than 10 seconds, which I would say is a bit infeasible. But when you start to add appropriate number of sub-batches, you can even decrypt large batches of more than 500 transactions in less than 4 seconds, which I would say is reasonable. And a nice property of the aggregation procedure is that it's actually trivially parallelizable. So if you use the correct optimizations, then even on a desktop or like a normal desktop machine with just 16 threads, you can decrypt more than 500 transactions in less than half a second. So the approach would be to just everything is efficient despite aggregation. So the approach would be to just have one fat node which carries out the aggregation and then just post the messages. So there, I want to mention there's also some concurrent work. There's basically 3 works which try to solve the same problems of removing this interactive per epoch setup from this original work, but they use a completely different approach, more or less related to witness encryption. They compare to us by being asymptotically more efficient in this aggregation step, but their ciphertexts are tied to a specific epoch. So they don't have this nice property that you don't need to know ahead of time which transaction which block your transaction will be inside of. And let's conclude with some follow-up or potential open problems. So in my opinion, the most important to make this more practical is to mitigate this aggregation overhead further. And I think most obvious approaches here are to use a more efficient PRF, which maybe doesn't need any pairings. And also you could, as I said already, there's this fat node, you could kind of try to outsource the aggregation to a very strong machine with lots and lots of cores. At the same time, all of these works require to set up the committee members with a DKG protocol. And this is not so nice because we really want a dynamic committee. So we want committee members to join and leave and kind of to reestablish the committee lots of times, maybe every epoch or every few epochs, and carrying out the DKG whenever that happens becomes prohibitive over time. So to this end, we have some follow-up work where we combine our work with the recent work of silent setup encryption, which allows us to completely adaptively start up a new committee without any interaction among the committee members required. And for this, we just pay with some small efficiency losses. And with that, thanks for your attention, and here's a link to our paper.
Thanks for the great talk and great result. How does your work relate to threshold batched IB? There was another talk at the main conference where they have this TBIB schema, and there is this batch parameter that needs to be known at encryption time. So you encrypt an IB, and then the decryption keys are generated for digest computed from the IBs in that batch. But there's also this batch parameter, which is a bit annoying because I need to know that at encryption time. So does your scheme realize TBIB without that batch parameter?
Exactly, yeah. That's what it does. So we don't have this batch. It's one of these concurrent works I mentioned. So interestingly, all of these concurrent works kind of have very similar approach, and their approach is completely different from ours. So all of these works have this property that you need to know upfront this batch parameter. And they model it in different ways, but in the end, you need it for all of them. And our work doesn't have this. And for this, we pay with more with this aggregation overhead, I would say.
Any other questions?
You said that you need pairings. Which punctured PRF are you using?
It's due to Dujmovic et al., I think from last year's Eurocrypt. And they present 2 PRFs, which we can use both of them. It's just based on pairings and some one-time setup. And one of them has basically linear setup in this domain size, and one, I think, quadratic setup.
Have you tried using homomorphic PRGs with GGM trees?
No. We can look into that.